Hello, and this is another part of the exam to review for Math 10N04, 12550. I'm Dr. Tatyana Khodorovskiy, and in this section I'm going to talk about polynomial and rational inequalities. So there's 4 topics that are on this exam: rational functions, polynomial rational inequalities, exponential and log functions, and beginning trigonometry. And in this section I'll talk about polynomial and rational inequalities. So with polynomial inequalities or rational inequalities, just like linear inequalities, the solutions are intervals or unions of intervals. And there's generally 3 steps at solving these, whether they're polynomial or rational. So the first step is to rearrange your function, whether it's a polynomial or a rational function, so it looks like this with 0 on one side. Now f of x can be a polynomial or a rational function. So that's the first step. If you have some kind of inequality which does not have 0 on one side, you make it into an inequality with 0 on one side. The next step is to factor. If you have a polynomial, you factor that polynomial. If you have a rational function, you factor the numerator and you factor the denominator. And then when you factor and determine the partition points of f of x. A partition point is where a polynomial is where a function may possibly change sign. It doesn't have to change sign there, but it has potential to change sign there. For polynomials, this is where the polynomial has zeros. For rational functions, this is where a rational function has a break in its domain or also a 0. And so the next step is to evaluate a test point or a test point between each partition point. So either you can take a test point between each partition point, or you can just look at the partition, at the entire interval in the partition as a whole, and decide whether the function is positive or negative there. So this is a general strategy for solving polynomial rational inequalities. So let me do some problems from the review sheet and from the homework. So the first example that I'm going to do is number 23 in the review. And this problem says solve the following inequality: x minus 4 squared times x minus 2 times x plus 3 greater or equal to than 0. So since this is already factored for us and one side is already 0, we can skip ahead to the third step and just directly look at the partition points and test each partition point. So you don't have to, but it's very helpful to draw a number line. The possible partition points here are as follows. The partition points are any time the function has the potential to change sign. X equals 4, x equals 2, or x equals negative 3, the very things that are going to make each factor 0. So then you draw these partition points on your number line, and then you look at every single interval in between. And when you're determining sign, the basic principle of determining signs is, remember what happens when you multiply positive and negative numbers. If you multiply 2 positive numbers, you get a positive number. If you multiply a positive and a negative number, you're going to get a negative number. If you multiply 2 negative numbers, you're going to get a positive number. You can either do this generally like that, or you can actually plug in a point. So let me look at the rightmost interval from 4 to infinity. I can plug in a point from there, for example 5, and see if my number is positive or negative. But I can just see that the first factor, if I plug in something greater than 4, is going to be positive. Anything squared is positive. If I plug in something greater than 4, x minus 2 is going to be positive. And the third factor is going to be positive as well. That means everything in this section of the real line from 4 to infinity is going to be positive. Next, I look at everything from 2 to 4. The first factor is still going to be positive because it's squared. X minus 4 squared, no matter what, is going to be positive. You can actually do this without including 4 as one of your partition points, but it's still best to include it just in case. Something from 2 to 4, if I plug into the second factor, is still going to be positive, and also for the third factor. So this is still positive. If I plug in anything between -3 and 2, and a good test point is 0, I can also look at whether I'm going to be positive or negative. So the first factor is again positive because anything squared is positive. The second factor is going to be negative. Because if I plug in something like 0, 0 minus 2 is negative. And anything less than 2, when I plug in there, it's going to be negative. The second factor, if I plug in anything between -3 and 2, is still going to be positive. So everything in this segment is going to be positive. And the last segment, the first factor is positive, and the second and third factors are negative. So I have a positive times a negative, which in return, I'm going to get a positive. Now in this problem, I'm asked to write when is this inequality going to be positive, and my final answer in interval notation is going to be from -infinity to -3, with a bracket because I have greater than or equal to, union everything from 2 to infinity. And so the final answer in interval notation is this. For all the values of x in this union of two intervals, this inequality is going to be true. In the next example, and this is from a homework exercise, we're also doing a polynomial inequality. This polynomial inequality is not factored and one side is not 0. So we're going to have to first do these steps. So in this inequality, we have -x cubed is greater or equal to -12x squared plus 20x. So what we first do is bring everything over to one side. It doesn't matter which side, but you have to pick one. In this case, I brought over x cubed over there, so I added x cubed to both sides of the inequality. Now, it's not factored, so I need to factor it. So now, first I'm going to factor out x, because there's an x in every term, and I'm going to get x times a quadratic. And now a quadratic I can factor. The quadratic I can factor further. This is going to be x times x minus 10 and x minus 2. So the partition points, the possible points where this can change sign, is as follows. It happens at x equals 0, at x equals 10, and at x equals 2. So what I'm going to do is I'm going to draw a number line with these partition points, 0, 2, and 10. And then I'm going to look at my factors and see how they do with their signs. So if I am 10 or greater, then I have 3 factors, and they're all going to be positive. So everything in this section is going to be positive. Next, I look everywhere from 2 to 10. If I plug in something from 2 to 10, x is going to be positive, x minus 10 is going to be negative, and x minus 2 is going to be positive. Again, you can either do this or you can take a test point between 2 and 10, for example 5, and then you plug in 5 times negative 5 times 3, that's a negative number. Everything in this section is going to be negative. Next, from 0 to 2, the first factor is x, that's going to be positive, the second factor is going to be negative, and the second factor is also going to be negative. Or you can take a test point, for example, x equals 1. So positive times negative is going to give me a positive. Finally, from negative infinity to 0, I'm going to get a negative times a negative times a negative, giving me a negative. So in this example, I want to know what is less than or equal to 0, and I want to write my solution in interval notation, so I'm going to take everywhere where the minus signs are. That's negative infinity to 0, bracket, I'm including 0 because this is less than or equal to, union 2, 10, and again I have brackets everywhere. So this is the final answer to this polynomial inequality. So first we bring everything over to one side, so one side is 0. We factor, get our partition points, draw those partition points on the real number line, and then play with the signs to figure out, am I going to get something positive or something negative. Also, just as a note, if you were to graph this polynomial, so if we were, as an aside, if we were to graph this polynomial as we were doing in the previous section, so if we wanted to graph x cubed minus 12x squared plus 20x, if this is a function that we wanted to graph, we'd also first factor it, and from the factors we see that it has roots on x equals 0, x equals 10, and x equals 2. We'd also see that what the end behavior says about it, this is an odd degree polynomial, so it should begin from negative infinity. And we know it's going to have a root at 0. So the graph of this polynomial is going to look like this. And I'm going to draw the parts of it that are negative. So everything here is negative. Everything here is positive. From 2 to 10, we are negative again. And from 10 and above, we're positive. So this is how the graph of this polynomial would look like. And this exactly matches what we have in our evaluation of the signs. Between 0 and 2, it's positive, and 10 and above, it's positive. Everywhere else, it's negative. So this is another way to double check whether your solving of the polynomial is correct. Next, we're going to do a rational inequality. The rational inequality in number 26. This is number 26 from the review. We're asked to solve this inequality. This inequality is already set that it's greater or equal to than 0, so we don't need to make it greater or equal to than 0, but we do need to factor it. We're going to factor the numerator into x plus 2 and x plus 3, and we're going to factor the denominator into x plus 1 and x minus 1. The partition points are anywhere the denominator or numerator is 0, exactly like the case with polynomials. So the partition points are x equals negative 2, x equals negative 3 from the numerator, and from the denominator, these are the asymptotes, but they're still partition points because the function may possibly change sign there. So we have 4 partition points in this problem, and we draw them all on the number line. And again, we play the same game with signs. I have a product and quotient of 4 things here, and again, the same rule of signs is going to apply. If there's an odd number of negatives, it's going to be negative. If there's an even number of negatives, there's going to be positive. So if something is greater than 1, then all 4 factors are positive, so I'm going to get something positive here. I can also take a test point. Next, if I'm between -1 and 1, everything in the numerator is still positive, and the only thing that turns negative is the x minus 1 term. So I have a positive divided by a positive times a negative, so this is a negative. Now between -2 and -1, if I plug things in, I'm going to get the denominator positive times positive. The numerator is positive times positive, the denominator is negative times negative, giving me something positive. Between -3 and -2, I'm going to have something negative times something positive divided by negative times negative, which is going to give me something negative. And finally, in the last piece, I'm going to get all negatives, and that is 4 negatives, that's going to give me a positive. Now I'm looking for where this is greater or equal to than 0, so I'm looking for where is this positive. And the final answer is -infinity to -3, union -2 to -1, union -1 to infinity. So one little detail here is that although this says greater or equal to, next to the partition point -1, I put a parentheses and not a bracket. And there's a reason for this. The reason is that this is a parentheses because x equals -1 is not in the domain of this expression. Something is not in the domain, it can be positive or negative. So that is the reason for parentheses there. So the final answer, where is this expression positive? From -infinity to -3, including -3, union -2 to -1, including only -2, and then from -1 to infinity. In the next example, this is going to be number 28 from the review. I have the following rational inequality. So this one is not factored and one side is not 0. And the only way that I can factor this, or I can start solving it, is if I bring the x plus 5 over to one side and make it greater or equal to than 0. The most incorrect thing here to do is multiply both sides by x plus 1. What you generally want to avoid when you're solving inequalities of any kind with variable x is never multiply or divide by something that has an x in it, because you never know if that x is positive or negative. If we multiply by a negative number, the inequality flips sign. So in order to avoid that, all the algebraic manipulations with inequality should be either to add or to subtract. Here we're going to subtract x plus 5 from both sides. This does not change the sign of the inequality. Next, we want to make it into a rational function. That's a numerator over denominator. So we need to put things over a common denominator. We're going to put everything over x plus 1, and we're going to be very careful with signs here. What we did is we put x plus 1 over the denominator, x plus 5 over the denominator x plus 1, and we can do so as long as we multiply both the numerator and denominator by x plus 1. Now we expand and we simplify. So this is 2x plus 17 minus, and be very careful with this minus sign. And then finally, we expand the minus. This is 2x plus 17 minus x cubed minus 6x minus 5 divided by x plus 1 greater than 0. Now we collect like terms, and we get negative x squared plus 4x, negative x squared minus 4x, minus 12 over x plus 1 greater than 0. Now we can multiply both sides of the inequality by negative 1. We don't have to, but it makes the numerator easier to factor. It's okay to multiply by a constant. The trouble starts when you start multiplying by a variable. So we multiplied by negative 1, and what we got was the following inequality. So now we have x squared plus 4x minus 12 divided by x plus 1. And now we factor. Now we factor, and we get x plus 6, x minus 2 over x plus 1, which is less than 0. And so the partition points are going to be x equals negative 6, x equals 2, and x equals negative 1. And the only way we were able to get those partition points is to factor everything. So now we put everything over the number line. So we have the partition point negative 6, negative 1, and 2. And again, we play this game with signs. So if everything is 2 or higher, this product is going to be positive times positive divided by positive, giving us a positive. From negative 1 to 2, we're going to get a positive times a positive divided by a negative. So actually, it's going to be a positive times a negative divided by a positive. Nevertheless, it's still going to give us a negative. And from negative 6 to negative 1, we're going to get a positive times a negative divided by a negative, giving us a positive. And finally, we're going to have a negative times a negative divided by a negative, giving us a negative. So the final answer to this problem is negative infinity to negative 6 union negative 1 to 2. Remember, from this to this step, when we went from here to here, we flipped the sign of the inequality because we multiplied both sides by negative 1. So the inequality ended up flipping here. So we are looking for all the values of x for which this is less than 0. So that is why we're picking up the negative ones. So this is it for the review on polynomial rational inequality.